Alright, today we're going to look at another one of these early integrated circuits, and I think this is something pretty interesting, pretty special. It is the 1KL10E, also known as the 564LE10, a Russian flat pack triple NOR gate. And you can actually see if this is a date code, which I think it is, 27th week of 98. This is a lot less early than anything we have looked at before. I'd hardly call this early at all. But it still has a place in this series because the design for this chip is very old. And it's also a fairly successful design if they're still making it in 98. So one thing that I think is very, very, very cool about this chip, and I'll just get it out of its protective wrapping here. I know people are going to yell at me for touching a CMOS chip with my fingers and stuff, but it's really where I live. It's not that much of a problem because there is a connection to the ocean right outside the window. Humidity never falls below whatever 60-70%. It's incredibly humid. There's basically we only have rain. It's the only weather we get. And I've never had any sort of issue with damaging stuff with static electricity. Anyway, here's the chip without its wrapping, and you can see this is a lot like the NOR gates that were used in the Apollo guidance computer, actually. It's the same sort of flat pack. The pin 1 is actually indicated by this little notch up here, which is common to, I think, all of these Russian flat packs. And if I put another one here, you can see the notches up there, but only because the chip is the wrong way around. So, pretty cool in itself. What makes this even cooler is that I think this has to be of a stylized rocket. I mean, I can think of no other interpretation of this symbol. This has to be some sort of aerospace designation, I think. Maybe it's a maker's mark, but I don't know which factory would produce this. And I've seen other examples of this with this sort of rocket marking on there. So I think this might even be designated for either use in aeroplanes or even for space applications. So this is pretty cool, I think. The nearest equivalent to this circuit is the CD4025. And we'll just have a look at the datasheet here real quick. Alright, here's the datasheet for the equivalent RCA type. You can see there's a couple different chips in this series. I think the coolest one is actually the 4000, which has two NOR gates and then just a bonus inverter down there, which I think is pretty handy. But the one we have is this one, the 4025. As you can see, it's just 3 gates and supply pins, so nothing to write home about. These are all CMOS, although the Russian one we have is not 20 volt rated, it's actually 12 volt rated. At least that is what the Russian datasheets say, as far as I could translate them. The datasheet here, there's nothing special, except for a block diagram of the actual sections. Well, this is 44,000. And this is for the 25. You can see this is just 3 discrete CMOS NOR gates. And then also some protection here. But really nothing all that special. What's very interesting is they give us die photographs here. As you can see, this is the 25. This is reasonably simple. The Russian datasheet says this has, at least the Russian version, it has 56 active elements inside it. So if we go back to this diagram here, you can see this is not 56 elements or 54. So either the Russian version is a lot more complex and just does the same function, which I think is probably true, or some of these things here are abstracted away and some of these transistors are actually multiple transistors, which I don't think is true because it says schematic diagram down here. Usually if they abstract it away, it says something like functional diagram or functionally equivalent. Alright, so what most of you are waiting for is obviously some actual circuits with this chip. But since it is in this SMD flat pack form, I first had to make a little breakout board. And this is just the footprint of the chip. And then it's sorted down and it's broken out to a row of headers on each side. So very basic. But because these flat pack chips are really quite wide, I mean, if I compare it to a regular TTL or a regular DIP package here, you can see this is really quite wide. I mean, with its pins, it's almost as wide as the equivalent DIP package is long. So we're going to have the problem, this is not going to fit into a standard breadboard easily. Decided to do is just to take some small breadboards, and I really like those small modular breadboards. I mean, you can plug them together. These usually come in very nice quality. The larger ones I had a lot more experience where the pins were really bad, but these seem to be fine. They're relatively cheap. So, and they're fairly modular. You can do things like this, which is we're just going to plug the one side into the one breadboard, and then we're going to plug the other side here into the other breadboard, and then we have this chip broken out to a breadboard. Alright, so here's the thing all hooked up. I've got the first two input of the NOR gate connected to ground, and then this is the various ground attachments. 2 channels for the oscilloscope, 1 for the signal generator and 1 for the power. They all go into pin 7, which is ground. We've got the positive of the power supply, which in this case is 6 volts, coming into pin 14 up here. And then I have on the output of the NOR gate, which is this, which is pin 9, I've got the purple trace from the oscilloscope. And then the input, which is pin 8 here, is going to the yellow trace on the oscilloscope, and that's also where the signal generator feeds in. So what we should get, since we have grounded these 2 inputs of the OR gate, we should just get an inversion of the input signal that we're feeding in. So I'll change the camera over to the oscilloscope and we'll just see what this does. Alright, here we are on the oscilloscope. The top trace is the input and the bottom trace is the output, and you can see it's a fairly clear inversion and signal actually looks quite good. This is at 100 kilohertz, so frequency is even relatively high. But if we actually zoom in here a little bit, you can see that's the input from my signal generator as well as the response is not perfect. Although I'm not entirely sure if this is an artifact from this being on a breadboard and signal being fairly fast, or if this is actually something that has something to do with the chip. So I don't think there's all that much more to say about it. I mean, it's an OR gate. It's not the most exciting circuit element. I just think the chip is really cool. because of the packaging and also because it has kept around as long as it has. I mean, they're probably still making these, and their design is really quite old. But that's the thing about the military. If the military likes something and they like using something, they'll just keep making it forever. And that's how you get vacuum tubes being used in equipment up into the 80s and 90s, where in civilian applications the circuit has been replaced by a transistor circuit long ago. But yeah, I don't think there's all that much more to say about it. I mean, I can crank up the frequency here a little bit. And we can crank it up to 2 megahertz and see what happens. It doesn't look as good, though, as said, not really entirely sure if this is about the signal generator or the circuit or the probing and my setup. If I go to a fairly slow signal, lower frequency, we go to 100 Hertz here, it looks perfect. Okay, here's an interesting thing. Did you notice that while I was explaining the circuit and the graph that we're seeing on the oscilloscope in the last bit, the voltage of the output kept getting lower and lower and lower? Yeah, I had forgotten to switch on the power supply. So what was happening there is the circuit was actually running off the output capacitor in the power supply, which it was slowly draining. But because it's a CMOS IC, obviously the current consumption is very, very, very low. So it kept running on the output capacitor in the power supply just for the whole segment. But you could actually see that in the performance at the higher frequencies. If I turn it up to 2 megahertz again, it's right on the limit of what my little function generator here can do. You can see it still doesn't look great, but it looks much better than before. And that's because it's actually getting the appropriate voltage and current that it wants. So if we go down to 1 megahertz here, see, this looks almost usable, as opposed to before where it's just looking a bit rubbish. So yeah, interesting thing here. Switch on your power supply if you're doing measurements on a circuit. That usually helps a lot. And yeah, it's quite interesting. The datasheet gives the current consumption for this chip as maximum 0.006 milliamps, which is actually quite low. Yeah, I think that's all I have to say about this particular circuit. I have a couple more of these Russian ICs lined up that we're going to have a look at, and maybe we'll do some more exciting circuits with these. But I think that's all for now. Thank you for watching, and if you liked the video, I'd hope to see you around.